Now let's see the bearing capacity factors. So bearing capacity are like they are the same. Whenever you have a bearing capacity equation, you'll have NC, NQ, and gamma. And again, I mentioned N gamma is different. That's why I'll start with the CFEM Canadian and the Canadian Foundation and the Canadian Highway Bridge, and I'll see what N gamma value equals over here. Just for info, these factors has been ideally have been determined based on modified plasticity of uniform ground condition. Okay, so that's uniform ground condition. Again, very high level. In real life, we usually don't have a uniform, or we might have a uniform ground condition. But if you have multiples, you just know it might be a little bit different because the brain capacity mechanism might be a little bit different too. But it's still applicable. We use that all the time, even if we have different layers. That's why I call this from theory to practice. So here we say it's uniform ground condition, but I'm telling you in practice we use that literally everywhere. There's no other solution basically because the variables will be unknown, like it will be infinity. So you can't have something else other than what we have over here. As of why in degrees, NCNQ has been reported by Meyerhoff, Hinson, and Visick. Uh, and there's a good stop over here. So NC and NQ and N gamma, usually they are not different between between the geotechnical engineering scientists, so they are almost the same. Canadian Foundation Engineering Manual and CSA, they use the Visick equations, which again they are almost the same as Meyerhoff and Hansen for the NC and NQ. So NC as equation, it's NQ minus 1 times cotan phi, which is gonna lead us to know we want to know what is NQ. So NQ is an exponential, and it's crucial that you know it's exponential. So NQ is e to the power pi 10 phi 10 square 45 plus phi over 2. So if you recall what does 45 plus phi over 2 is, let's go back to the first slide just to show you what is this. That's this angle. 45 plus phi over 2. So 10 this angle, which is 10 alpha. Let's say it 45 plus phi over 2. Nice. So now we know NC and Q gum. Again, if you know phi, you go to like either a table or you just substitute in this equation, you will get NC and NQ. Very straightforward. Now let's see N gamma. So Canadian Foundation Engineering Method chose to use a more conservative N gamma, which is the gamma that's determined based on Davis and Booker in 1971. I'm gonna say why it's more conservative, because when compared to the H2, N gamma over here is less than what H2 is using basically. So in gamma, it's again it's exponential function, all to the power phi. So all of them are exponential. So NQ is exponential and NC is a function of NQ. So you can see it's all exponential. Almost 0.1054 exponential 0.167 times phi. Now let's see this figure, which is basically the NC, NQ, and gamma. So again, you can just substitute in this equation, or okay, let's see something NC and gamma in Q. So if you have phi equals 0, that's why I'm saying it's straight function of phi. If you have phi equals 0, so at 0 you will get NC equal, that's memorized, 5.14 or 5.1, and you don't have NQ and N gamma. If you have N gamma equals 30, you get N gamma and NQ and NC as well. Nice. So what I just want to highlight over here, you see how N gamma almost after 33 or something, it just increased very high. Like it's at the bottom of the curve up to a certain angle of friction, and then it's flying. It increases very rapidly, and it's actually this equation. So N gamma is like very important, because if you choose 33 or 35 instead of 36, you might get like a 20% increase in the brain capacity. N gamma has a huge significant in the brain capacity calculation. That's why there's like There's no agreement between the scientists what is the real value of n gamma, and everyone is saying a different thing, but we just follow the code. So Davis and Poker in Canadian Foundation and CSAS6, and that's the equations that you will use. And here I have a question for you. Why NC, NQ, and N gamma are sensitive to the small change of the friction angle? And I'm telling you, and look at the equation. So I'm actually giving you the solution. So why is that? Why any small change is very significant? I think it's very clear. Like here, you see a very mild slope, especially after 30 degrees. And after 30 degrees, wow, it all rise up very rapidly. So small increase, small increase, small increase, and all then goes up very high. So it's simply because of the exponential term, and that's literally the definition of the exponential term. You start with a very mild slope, and then it's exponential, so it goes very high very fast. What is behind this question? Just make sure what value of y you're gonna use. So we will not be subjected to this in the course, what phi to use based on the different soils, but I promise we will go somewhere at some time how you choose the appropriate soil properties or CNFY. It's just a big topic which we shouldn't be cover at the same time as the bearing capacity. But you just know if it's 35 and you are in doubt between 35 and 36, please choose 35 because it will give you a more conservative bearing capacity. Okay, now same things. Instead of using this equation, you can use the table, and these tables are available in the Canadian Foundation Engineering Manual. And I just plotted them over here. And I'm just giving you an example. At y equals 0, as we said, NC equals 5.5, NQ, and in N cube 1 in gamma equals 0, and N gamma equals 0, whatever rough or smooth. What does rough and smooth mean? So rough surface is a surface between the footing and the soil, which means the footing or the concrete footing is cast in place or cast directly on the soil. That's the rough interaction. And that's why you see the rough interaction is more or almost double the smooth interaction. So if the soil is, if the foundation or the footing is precast, use the smooth surface. Usually for bridges, CSA doesn't recommend using precast slide or precast footing. Not in general, but it's not the best. It doesn't give you the best value of just place the footing. If you wanna make everything else precast, it's fine. But the footing, just please cast it over the soil. It will give you a lot of more friction, and gamma will be a more higher. And yeah, straightforward. And yeah, now let's see for phi equals 30. By the way, these numbers, phi equals 0, phi equals 30, that's the two examples we will use throughout the course. That's why I'm highlighting them over here. Nice. And here we go. Now we have the n gamma value. Okay. Now I'm telling you, as I told you, n gamma is not unified between the different scientists, and it's huge. It's pretty big thing. So there are different equations. We have Beers, Booker, Martin, Marhove, Hejiaj, and Hansen and Visk. So the most famous three are Marhove, Hansen, and Visk. And the difference is quite significant, by the way. See the three of them. It's just very significant. So that's why you just stick to whatever your code tell you. So for the Canadian people in Canada who are designing for a Canadian project, that's the equation you're gonna use Booker 1969 or 1971, and just use phi in radian. And because phi in radian over here, it's not the same equations that I presented before, so it's 9.65 prime, but phi in radian. Or if you go back to the n gamma that I showed, it's 0.1675. So it's different because here's a phi in radian, but here's a phi in degrees. Okay, just make it straightforward for you. Use phi in degrees. That's what I'm telling you over here. So phi in this equation, in all of these equations, are degrees. Now, if you go to the Ashtot, use Vesic equation, which is a lot more. and I'll show you the comparison in the next slide. So that's this equation 2 nq plus 1 10 phi. So there's kind of like, it's a little bit weird because the Canadian Foundation Engineering Manual chose to use NC and NQ of VESIC, but then for the Ngoma, they use Davis and Pucher. Again, that's more conservative, okay? So I'm fine with that, to be honest. But in the H2, you gonna know that you have a bigger Ngoma than the Canadian Foundation Engineering Manual. And both are okay, because that's has been created for the Canadian industry, the whatever the industry is knowing and whatever the industry is using, and the H2 is for the US and actually internationally too. Okay, now that's the different equations. Pierce, Poker, Martin, Marhov, Hansen, Vesic. I just want to see Hansen, Marhov, and Vesic. They are very close, so not that far, except for Vesic. Vesic is like very high. I'm gonna delete this 56.31. I don't know what is this. Okay, so for the CFEM at phi equals 30 degrees, if you're gonna use the Canadian, you're gonna take Ngama equal 15.1, but if you're gonna use Vesic, it will be 22.5. Now let's go to 40. So if you go to a very high friction angle, 40, Booker is like 80, Marhov is 85, close by, Hansen is very close to Marhov, 85, but Vesic is 110. So that's significantly changed. That's like something around 30%, 40%. Yeah, something around 40% increase just in Ngoma. Here you have a little bit of increase. Instead of 15.1, you have 22.4. And again, it's just where your project is and what your specification is. And I'm here just to tell you there's a difference, and now you know the difference and you know how to deal with the different values. Marhova and Hansen, I just noticed now. I didn't prepare for this, but just looked at the equation and they are very, very close to each other. So it's something good, especially at like low bearing capacities. Yeah, again, if you go up because it's exponential, you will find like a lot more difference. Okay, H2. H2, I said NC and NQ are the same, so that's why NC NQ minus 1 10 phi NQ equal E pi to the power pi 10 phi 10 square 45 plus phi over 2. That's equation 7. And now you know N gamma is the basic equation, NQ plus 1 10 phi. So if you go to phi equals 0 and gamma equals 0, at 30 you have 22.4, and at 40 you have 110. Same with what we said before. And again, 0 and 30 are the two problems that we will solve throughout the course. So just remember that in gamma from the H2 equation is 22.4.